Right, and in this video, I will discuss the I2C, SPI, and serial wire communication. So, I2C stands for Integrated Speed Protocol. Serial Peripheral Interface, SPI stands for Serial Peripheral Interface, and then we have serial wire communication. Serial wire communication kita discuss the DST11. Okay, integrated actually I2C developed by Philips in 80s, and then followed by the Motorola for the SPI. Actually, the I2C SPI is serial communications where I2C require only two wires, which is serial clock and serial data, included with the VCC, DVP and ground. And then SPI requires four wires, which are serial clock or data out, serial clock, data in, chip select. So the way SPI access or the master access SPI devices is use the chip select, but the I2C in the I2C the master access the device by the unique addresses. So and then for the I2C we can have more than one master, but I expect only one master. So that is the difference between the I2C and SPI. On top of it, the SPI is faster compared to I2C because SPI the data we have two wires for data in and data out, but in I2C we have only one wire for data in and data out. The wire right? Okay, to connect the device, I2C device to the master or to the controller, we need the pull-up resistor to pull it up. And then the clock can be connected to clock in parallel and give data to the data line to the data lines of other devices in parallel too. The size for the resistor, can be 1.8 up to 15 kilo ohm. But normally I use around 5.1, 5.6, right? 3.6 kilo ohm. But it's reported that the resistance of 2.2 kilo ohm is enough. And next, if we have numbers of devices, we can have only two pull-up resistors, no need for us to fix all the resistors. Right? But when we bought the breakout module, normally it comes already with the pull-up resistor. So no need for you to take them out. Here we say one master and few slave, SPI for the I2C, because we can work more than one master, but complicated. It's complicated. For the I2C protocol, I think this one you can read, it. Very simple. This is what we talk about, how the data comes in, and then in serial, then the data converted to parallel, and then when the data is completed, then you are complete by the controller, right? And then the system clock, right? The clock, the duration from here. This is two data. The most important things in the I2C is what the start condition and stop condition, which is the way how the data can be recognized by the device. So the SD for the start conditions, the SD is pull up, pull down, while SD is go high. Okay. Then followed by SCLK pull down. That is recognized as the start condition. So in idle, SD and SCLK at high. Then for the stop condition is the SD is too high, when SCL is at high, and that is start collision. So the data stream look like this. So we have start collisions and then followed by the stop collision here. Stop collision here. So the data is sent by MSP first, most likely. So the first one is the slave address. So for the I2C, as we talked before, all the devices synchronized by the unique address. So different device, different slave address. So the address can be 7 or 10. 7 or 10. This depends on the device. So if you got it, you need to read the data sheet to find out what is the target. The address for that device. And then followed by R or W bar. R means read, W bar means write. And so here we can see that when the last bit is 1, right, then it is for reading. And if the W, if it is 0, that means for writing, right? And then followed by the acknowledgement by the either device, and then followed by the data, and followed by acknowledgement by the slave or the device, and then can be any other data. And up with the acknowledgement and stop. So that the way how the data is being sent by the I2C. So in detail, you can see, for example, for the DS1307, the time clock. So for the real time clock, we put the pull up here, right? Pull up here for the SCL and SPI, and then we have a crystal, external crystal. If I'm not mistaken, the crystal is about 52.726 locus. And the one, you need to read the data sheet for it. Then we have the same clock here, SPI wave generator. Here we can generate the SPI wave if we like. There is another the one of the options that available in the S1307, but we not discuss about it, right? Okay, so the S1307 is a RTC, real-time clock. So it can provide the data for what seconds, minutes, hour, date, month, and year information. This is the address inside the address for the DS1307. Right, start with 0, address 0. This is address is not given, is given by the Dallas, the manufacturer, not by us. So address 0 is the second register. So the information of the second is inside this. On top of it, at pin 7, we have CH. CH is what? CH is for enable or disable the clock. Right? So we have a clock here, right? Huh? Oh, yeah. Okay, so here we have what? We have the. Okay, we have a clock here, right? We have a clock here. So the clock we can disable manual by bit 7. This bit 7. Right? So if the bit is 0, mean we enable the clock. If 1, mean we disable the clock. Next we have what? Next we have a minutes register. Then we have hours register. Okay, on top of that, we can have 24 or 12 hours. Or PM, AM, then we can have a day, month, year. Right? And then for 07 or register, the 7 is a control bit, a control bytes, and control words. Normally we call it as control words. Control words for what? For the SPI wave generation. Right? Yeah. But the one I not discussing. Then we have 08 up to 7, 3F is about 56 RAM. Right? The RAM, that's for user data. Right? It is what? It is non-volatile. signal voltage expand. Means the data will not lost if you take out the power. Take out the power, the data will not lost. It is static RAM. It is static. Okay, how the data is transmitted. For the DS, we start with, you see here we have set S, this means start, generated by the master, right? Then the master will address the device. So the address for the DS13107 is 1101.000, 7 bit, 1101.000, and then followed by 0 means the control the master wants to write the data. Means it signifies what? That the master wants to write the data to the device. And then acknowledged by the device. And then the master will place the first data. Right? Which normally is what? Is the address or address of the register that the master wants to write the data. And then followed by the data, acknowledged by the device once received, and then followed by another data, acknowledged by the device, followed by another data, until the last one. If the master don't want to send more data, then we will say what? P. P is the stop function. So that's the device that no more data for you, right? For the slave in receive mode, then first the master will send the S and followed by the address and followed by 1 for RF or W bar read. So 1 mean what? What mean read? So the processor want to read the data. And next, then the processor will then acknowledged by the process the DS1307 device, and then the device plays the data, and then read by the master. After read, then the master will place acknowledge. We give the acknowledge bit. Next, then the device plays in the data, and then place another. Then the master will acknowledge. Then place in the data by the device and acknowledged by the master. Follow in that manner. Last, if the processor doesn't want, or the master doesn't want more data, then we place acknowledge, not acknowledge, or A bar. Not acknowledge means I don't want more data. Then and followed by stop bit. Stop bit still generated by the master. Remember, stop bit always generated by the master. Start and stop always by the master. Clock also generated by the master. Right? So the device follow the clock generated by the master. Okay, so this is another way data transmit and receive mode. That means if I want to read data from if the master want to read data from say register from register what? From register, say from register unit. So the address is what? 01, right? 01. 01, so the processor will place first, we place S, start, and then followed by the address, and then 0 for writing. To write what? But once acknowledged by the device, then the processor will place the first word's address, which is the address of the register the processor wants to read. So 01. 01 because I want to read data from unit. Then it is acknowledged by the device, and then the processor will place SR, repeated start, ataupun restart, restart again means. Then place the address and followed by 1, mean 1 to read, right? 1 to read. And next, the device will at least is acknowledged by device, and then the device will place the data, which is the data of meaning. And then automatically the address of the device or the register increased by 1. That means now it's point to hours, right? Automatically, then the device plays the data, which is data of beginning, because the address register is increased by 1, and then read by the master and master acknowledge it, right? If the master, because the master acknowledge not acknowledge, then the device will place the data. What's data now? D, because the register increased by 1. It's automatically increased in that way until the last one. When the processor doesn't want more data, then we place A bar or not acknowledge, and then followed by B. Right? That's the idea. It's very simple, right? It's simple. So to connect it, don't do like this. Okay, first you go to your SNQ MX, right? SNQ MX, then set your I2C connectivity, right? You can select. We have, I think we have 3 there, right? I2C 1, I2C 2, I2C 3. So if you connect to I2C 1, select I2C 1, then in the mode select I2C, because we have link and so on inside. Okay, select I2C, then in it's automatically that generate for you the I2C. I can see it, but I think this one is PV6 and PV7, right? PV6 and PV7. Then, so PV6 is for what? For SCL, and PV7 is for SPI. Then you connect it. Right? So this is PV6, right? Go to SCL, the green color one. That's also the green color one is green one. Okay, good then. Salah. The salah tu. What? The green color should be ground, and then the purple should be 7. Kalau you follow this one, salah. Okay. Good person. Okay, next. After that, then you set the I2C. So set them on, because this device it can work around 180 kilohertz to 100 kilohertz. 80 to 100 kilohertz. So set to center mode, so you can reduce your frequency if you like. Then others just especially primary address is 7 bit. Remember, our address is 11010000 7 bit, right? So the primary address is 7 bit. Then after that, how to work with the DS1307? First, we enable the time picking, right? Time picking. CS1, the bit 0, bit 7 in register 0 must be 0 to enable the clock picking. Next, set time. Of course, right, when you use your watch, then you set the watch, right, for the first time, right? Then at interval of less than 1 second. Interval less of 1 second, then we get the second. Then in the second change, then we look at it. If bit 7 is 1, then we need to reset. Because it means that something wrong. It is not what. Then we simple that the clock will be off. So you need to reset CS0 if CS is equal to 1. Else, then we read minute, then we read second, we read second, minute, and then hour, and then display. That's all. Right, very simple, right? Okay, so the code principle here, I use HAL I2C master. We have two, right? HAL I2C mem and HAL I2C master. You can read it in my book, right? Chapter 7. Chapter 7, I provide the driver. So there are 2 types of driver, or 2 types of HAL I2C that we can use. Master and memory. better memory. Okay, but for this one, because of the simplicity, I will use the master. Right? So the first one here, we want to write data into what? Second address. Right? The first one, second address. So we place the address into RTC buffer 0. Buffer 0. Then RTC buffer 1, we set bit stable to 0. Right? You see 0, 7, 7, 7, 7. We can set 0 if you like. Don't care about it. Alright? Then we use whole I2C master transmit to transmit to where? To I2C 1. What? To I2C 1. Through I2C 1. To I2C 1. To where? To the S1307 address. Then we need to see it by 1. By 1. When you see it by 1, 1101 00030. Then we can what? 1101 0000. Then you see the last bit now 0. Maybe we want to write. Right? What we want to write? The value inside the RTC buffer. The data inside the RTC buffer. How many that? 2. Right? 2 and then followed by 50. 50 is the time wait. Then after that we want to set the time. So I want to set the time to 2, 10, 15. Remember the time is in hexa, in BCD, binary coded decimal. So we place 2, 0x, 2, 0x, 10, 0x, 50 for hours, minute and second. Right? Which address should we start? You should start at address second or 0. Right? So the address must be second address. So to set time, we send 4 data, which is the first address to be right, in the return. Then the data for minute, a second, the data for minute, and the data for hours. We have 4. Okay, then after that, in the loop then, so each time the time out, I say less than 1 second, because the second is generated each 1 second. Right? Maybe you can set it to 300 milliseconds, maybe you can set it to 400 milliseconds. And then what we do? We read the signal. We want to read from what? One data only. One data only. From where? We want to read from second. The rest off. No, we want to read it and place it into second. Second is the variable. So we set only the address of second 0. Address of second 0. We not send the variable, but the address of the second 0. Okay? So from here, you see, we set the address, then we read. Then we check. If second one not equal to second 0, means what? There is a changes in the address the second register, right? So if there is change, then we first we check if second 0, bit number 7 is 1, then something wrong. So what we need to do? Then we write it to 0. We write it to 0, that's all. Right. Else that we copy that second 0 to second 1, because it's not change. Next, we can read this one. Basically, this one you can read only 2, minute and second. But I read 3. But if you want to read from minute, then this all I2C master transmit. I2C must be ampersand, not second address, but minute address. And then this one, RTC buffer must be 2, because you want to read minute and hour only in that for the idea. But this one, I read all the 3. And then I print it. That's all. Very simple, right? Okay, so you can read. If you try it, you get it. This is I2C for the BS1750 mapping. Right? It's just what? It's just the sensor that read the intensity of the light. Through what? Through the dark current. Dark current. Baca tentang foto diode. So the dark current feed to the amplifier and filter, then feed to the ADC, Then we have the internal controller, it will process it. This is one example of smart sensor. We call it smart sensor. Smart sensor means what? It can send data. It sends what? It convert the signal, or convert the language the signal, right? And convert it, then process it, right? Process it, save it, and then transfer it if requested. That is smart sensor. So nothing about it. Actually, it is it can detect light over 1 to 6.5, 35 lux. LX means lux. Lux means the intensity unit of intensity. And another unit of intensity is candela. Ada nggak candela? Right. Okay, this is the measurement procedure usually in the data sheet. So you can see we have once we set the power on, then we can select either measurement command, either one-time measurement or continuously. If one time we do it, and then after that we need to power on again to another. If you set it to continuous measurement, then you can continuously read the intensity of the sensor. Okay. And next, this is some of the instruction sets inside the BS1750 data sheet. We have two types of reading. H means high resolution, L means low resolution. And you can read some of the combination inside it, right? Okay, so we have power down, power on, please check the continuous H resolution mode 2, blah blah blah, and so on. Okay. So this one is higher resolution. See, mode 2, 0.5 lux resolution. 0.5 lux resolution. This one is 1 lux resolution. So better 0.5 lux resolution. Right. Okay, so this is the way how we from this then I write some sort of like what the sequence. I convert it into sequence of the first send continuously has resolution mode instructions. So we say what? Start SP sample start, then the 0001000011, and then followed by 0. So this one is the address of the BS1750, and compared to BS100, we have 11010000. This one is what? 01000011. Right? So that is different, right? The unique address. And then acknowledge. Once acknowledged by the device, then the processor will place the instruction set. So this instruction is what? Continuously hash resolution mode. Right? Continuous hash resolution mode. 0010000. 001, see here? 0010000. This one, right? 1, 2, 3, 4. Right? 4. So that is the data that I walk through the BS1750, acknowledged by the device, and then it start SP. Now SP, right? Simple tadi. Wait to complete 1 execution mode, approximately 1 day. So means delay, that delay, and then we can start the reading. Right? We can start the reading. So how to read it? Start read, followed by address, follow for read 1, right? For read write read is 1 for reading, and then acknowledged by the device. Then the device will replace the IBAT, right? IBAT, then acknowledged by once received, acknowledged by the master, then the device will place the low byte, and then not acknowledged by the master, and then the master will send the copy. That's all. Once you got the result, sieve that high byte by 8 bit because it's high byte, and then place a plastic with low byte, and then divide it by 1.2. So that is the resolution. That is the intensity required. So this one's from 2, right? Oh, saya punya ni semua salah. Okay, so set that one, then put the I2C. If maybe you want to use I2C too, up to you, right? Then connect the wire accordingly. Okay? And then write code, right? The first code here is for power on. First one, remember, we have power on. Then we can reset data. Maybe there are some data inside, reset all the data. Then after that, then we set to continuously, distribution mode, right? Then, when the time out for 500 milliseconds, then you read, I2C master receive, you read to read, right? Then we have ES1750, ini the data is inside ES1750 data. So then the data alpha and robot they receive, then after that, then we convert into float, right? And divide by 1 on 2. That means very simple, right? Okay, so that's the result. Okay, this one I don't want to talk more. Okay, this is you can read it, right? You can read it. Okay. So the way to understand the I2C, actually you must understand the LCD at the time 16 LCD. You don't understand it, then you don't understand the I2C LCD. Okay, next if we go to the SPI communications. So SPI communication we have 4 lines, 4 wires. So included with the machine ground, then we have 6 wires. So the way is the processor access the device is by the chip select part. Means that to access chip select must be pulled down and pulled down. So the words accepted, the chip select may pull down the chip select. Okay? So data is transmitted via serial data, SDO, and data is received via serial data in SDI. And then the synchronization of the transfer data is synchronized by the serial clock. So the serial clock is deleted by the processor, not deleted by the device. And you can divide different lines to send and receive data. So it is faster compared to I2C. Right. Some importance that I read it before, but I'm not really about. Believe. So the data for expected can go up to 4 gigabyte, 4 gigabit per second. 4 gigabit per second. That's all. But our processor works up to 10 megabit depending on second. We can check the data sheets. Alright, then it's very not really okay. Of course, it's not difficult to make address. Alright. So this is what we call keep the data and standby. So first the SS must be pulled down, right? Then the pull up the clock pull up and pull down, then the data can be received and transmit by the SDO and SPI. That's the way. The most important thing is the communication mode. We have 4 communication modes. 4 communication modes in the SPI. First one we have mode, this one we call it mode 0. Mode 0, so you see the pattern, right? You can see the pattern there, right? So this is straight clock idle at low, right? Idle at low. So mode 0, mode 1, this is mode 2, and then this is the mode 3, right? Mode 3. Are they different? This is 2, right? 2 bit. So this is 2 bit. This one is 1 bit. This is 1 bit 2. Right? So that's different. So SIPO must be 0 and SIPA must be 0 for mode 0, and SIPO must be 1 and SIPA must be 1 for mode 3. Right? That's different. So I said it's very important. This is very important. So we want to work with IDSL 325. And 3 axis accelerators, right? your line, right? Your line. Your line. So the connection, this is connection. So check between the connection, right? And this is correct or not. Next, this is how the 4 wires. We have the 4 wires right and read protocol. And this is the timing diagram. I think no need for me to talk about it. Right? It's too technical. This one is what data format addressing and operation. Clearing SCLK data format register, select for wire mode, where SCLK, select the wires mode. Okay, so we have 4 mode and 3 mode, 3 wires and 3 wires mode. Sometimes because for I2C too, and sometimes we just for this, for I2C too, sometimes we need only 2 transmit. Sometimes we need only 2 receive. Same with user. Sometimes we need only 2 receive. For example, when you use the what sensor is that the RFID we use only receive. There is no transmit. Right? No transmit. Once the RFID detect the tag, then it will generate the signal or the data to the processor. So the processor will read only the data. Never processor write data to the sensor. So you can read this one, right? Start to initialize the ADSL. This one you need to read the data sheet, then you can understand it. Put ADSL 345 in standby mode. Select range. Select data range. Okay, select range. So that is the register. The register. So this is the register. Right? You can see the register. Very small. So you need to get the data sheet and read it. Understand? So this one first we put ADSL into standby mode. Then we select range. Why do we put it into standby mode? Because we want to set the range, set data and so on. It must be in a standby mode. Kalau dalam reading mode tak boleh. Operation mode tak boleh. And then select range in register 0x31. Then set data date, data rate, and data rate. How many? The frequency. The frequency the data generated. And then put ADSL 345 into measurement mode 0x30. Same register, right? If you want to set the range and the data rate, you must what? Put it into standby mode. Put it into standby mode. And then to read, we get all 6 bytes. We have 6 bytes. 6 bytes. You set what? You set address 32, 33, 34, 35, 36, and 57. 34. Ready? Okay, 34. I think this is the data. And this one. 34, 35, 36. This one. Right. Okay, register to see. By which rate? The rate. You can set the rate by selecting the lower label, right? B1, B0, B1, B2, B3. So you need to read it. Bottom one, read it. Display it. Okay. So at the top. Okay, next we rearrange the receive data. So the receive data actually we have what? For X, X axis, Y axis, and Z axis. We have 3 axes. So the first one 0x32 and 0x33. 0x33 is a high byte for the X axis. High byte. That's why 0x33 must be what? C by 8 bit to the left and added to 0x32. Added to 0x32. Same with Y axis. So 35C to the left for 8 bit and plus with 34. And then multiply all the parameter with resolution scaling. So you need to know what is your resolution scaling. Multiply it. Then you got the result, SP. So you can see SK is equal to X multiplied by resolution. So resolution we need to read the data sheet. Right? What is the resolution that we use? Okay, so set up project with blah blah blah, follow it, right? Select prescaler to ensure the baud rate frequency less than 5 megabit. Why? Because the ADSL works up to, if I know the second, up to 5 megabits. So if you work with 4 megabits, okay. If you work with 6 megabit, maybe okay, but manufacturer not guaranteed. Right? That is the standard. No guaranteed. Manufacturer guaranteed it. It's okay as long as you work with 5 megabit. And then remember that when you read the dataset for the SPI, look for the mode of operations. So the mode operation for this is mode 3. Mode 3. Mode 3. So SIPA, SIPO and SIPA must be 1. Must be 1 and 1. That's the most important thing when we talk about what we work with the SPI. Okay, next we go to the. Okay, now we write code. Right? The code is simpler compared to I2C. The code is simpler compared to the I2C. Okay, so this is code for what? This is to write. Right. So to write, we need to prepare data to transfer. Okay, this is multiple write. So this is multiple write. 0. When you all use 0 as 0 for bit 6 1 is going to write multiple data. This one. So this and then add the address, and then data 1 is the value that you want to write. Right. And then assets will yes. Remember when assets in technical means what? Means enable. For our case, select bar and CS bar. Maybe it must be low. Next, just all SQL transcript data over to 100. So 100 is I'm waiting. I no need only to put 100. Just put 1 is enough. Because the speed is very fast. Right. Can you compare 1 megabit and 1 millisecond? Oh, it's 1 million different, right? 1 megabit and 1 millisecond. 1 million. 1 giga different. 1 milli? 1 million. So 1 giga, right? Different. So you can put 1 if you like. And then we accept your CS. Jangan dia, you write, you put down and then you jar. Tak boleh. Bila you nak write nanti, you write. Dulu you write. Dulu you do. Right? Okay, for reading then, okay. So this is receive buffer initial, this is data that you want to receive. I mean the buffer, this is the buffer. Right? This is the address for read operation. For read operation, you need to set bit 7 to 1. Right? The 7 must be 0. Next. Okay. Next then, we check for the to write the number. If the number means if you want to read more than one, then we need to set bit 6 to 1. So all bit 40, right? All bit 40. Then pull down your CS, then transmit the first one, the address I want to read. The address that I want to read. So that is the address. Then followed by reading. So you read it after that. Okay? And then you access your okay. Then you access your CS. And they said main pull-up. And then what? Then put all what you read into your result. Because the result I. So where's your result? This one, right? So you just pass, remember, you just pass the address of your result, not the result. The address of the result, not that buffer or that variable. Right? Okay? So you got it, right? So this one, I equal to receive buffer, I multiplied by 2 plus with 1, 6 multiplied by 8, or we receive buffer MSL I multiplied by 2. Maksud? Means that you take 2 because you letak in byte, but you receive in your identity or the word. You combine 2 bytes into 1 word. Combine 2 bytes into 1 word. Right? Then you got it. Okay? Next, you initialize. This is the initialize. Remember, reset all these, then forward command, and then set your range plus minus 40. So your range determine your resolution. Your resolution. Remember, your range determine your resolution. So that one you need to read your data sheet. Then set data rate to 1 hertz. That means that each 1 hertz then I got the data. Get the data. Or the response is 100 hertz. 100 hertz is what? Can you use it? Can you use it? 100 hertz. 1 to 100 what? 100 is what? 0.001, right? Okay. Next, and then this is second complement to decimal. Second complement to decimal. This is how to convert it from second complement to decimal. That one. Second complement to decimal. You know what is second complement? For example, you have 255. 255 actually it is minus 1. 255 it is minus 1. Because 255 is 1, 1, 1, 1, 1, 1, 1, 1. So the first one means what? Means negative. Then you convert all that, then you got 0, 0, 0, 0. Then you plus with 1. Then you got 1. It is minus negative 1. And if you have 1, 1, 1, 1, 1, 1, 0, 0, it is negative number. This is negative number. Why? The first bit is 1. The first bit, not the bit 0, it is 7. Then you invert all that, you got 0, 0, 0, 1, 1. Then you add it with 1. You got what? 1, 0, 0. Means it is negative 4. So 1, 1, 1, 1, 1, 1, 0, 0 is negative 4. So this is what the function does. Right? This function. Right? The last function. That's all. So place in the code is the word. Okay, no problem? Now, so you got like this. When you move your equation, then you got the result to be like this. Right? Okay, you see here, I multiply with the 0.0078, the resolution. Because my resolution is 4D plus minus 4D. And this one. And then I multiply with this 0.0005. Why? Because I want to have 4 point number. 4 point number. 0.755665. So to rounding it, rounding, let's say 0.5. Yeah, you have 0 point something, right? 0 point something. Rounding it, 1 point number, then you must add it with 0.05. Rounding it. Right? Okay, serial wire interfacing. Serial wire interfacing is another technique that now become popular. It's popular. Also, it based on the smart sensor. The smart sensor is a power sensor. Smart sensor means what? Produce the signal, process it, and then transmit it. Then transmit it. That is, so it reduces the wires. It reduces the wires. So the smart DC level is what the temperature sensor, humidity temperature sensor, right? So to connect it, just need one wire and pull up that wire, that data. So the data can be out or in, input or output. So look at the protocol, right? The transport protocol. What is transport protocol here? We have the first one, the red color. The red color is to start the relay level. Okay? So to start the device. So you pull down about what? Okay, the detail you need to read. The detail. Pull down and then pull up. Pull up and then wait the response from the device. Pull up and then the device will pull down and pull up. That is the response from the device. So this is transmit by the processor and receive by the processor. Right, the second one. And then after that, after the response, then the what? The device will place the data. Place the data. So if we place the time, depends on the width of the data. 0, 1 is depend on the width of the signal. The width of the signal. Okay, so this is the detail for the start and response timing. For the DST, okay, this one is at least 80 milliseconds. So pull down about 80 milliseconds, 20 milliseconds up, right? 20 milliseconds. Then after that, pull up, and then wait for the response. The response you will receive it around 20 to 40 microseconds, right? Microsecond. Microsecond. And then the DST will pull down about 80 microseconds, the response. And then pull up again about 80 microseconds. So that is the response. Means what? Means what? Means the DST is over there. Means the DST is over there. If you do not receive response from it, just like artist, right? No response SMS, no response come to class, response. Then after that, we will start the data transmissions. Okay, the data transmission, so the logic, logic 0 or 1, the indication, right? So you see the width of 1 here. If the data is, the width is about 26 to 28 microseconds, that is 0. If the width is 70 microseconds, about 70 microseconds, then it is 1. So now, if we check about, let's say about 40 microseconds. 40 microseconds after the signal change, right? After the signal change. So we can detect either it is 0 or 1. The green color 1. The green color 1. Can you see? The green color 1. If you check it at that point, if you got 0, means it is 0. If you check the point, if you got 1, it is 1. Very simple. Then pull data into the system. Okay? So, because we need the what? The precise time. For that reason, then we use a timer for the what? The time delay. In clock, and we use not in polymer. So I use a timer, time 6, right? Time 6. Activate. We can use time. Better you use for hours. This one I think L053. For hours, better we use timer 10 or 11 because we use what? 401. And F41, better you select timer 10 or timer 11. Okay, so the prescaler is determined, right? This one is determined. Okay, it's very simple. It's very simple. If your frequency, you work at say 80 megahertz. So if you divide it by 80, mean 1 peak is 1 microsecond. Right? 80 max divided by 80, you got what? 1 mega. 1 mega, if you invert it, then you got 1 microsecond. Okay? So your prescaler, for example, if you set your processor frequency at 80, so this one must be 80 minus 1. 80 minus and minus 1. Then this one, you can put it to maximum. Up to maximum. Say 6.535. Okay, or you can put to 0x FFF minus 1. Because we have 60 bits. If the 2 bits, then you can put 0x FFF minus 1. Okay, that's for the timer. So the timer we can use, okay, this one. So remember when you use timer, you need to enable that timer. In polling mode, as the phase start, emphasize the handler, timer handler. And then you can have the delay microsecond functions. Static for delay microseconds, UIT16_T X. So X is time delay in microsecond. So first clear the value inside your counter, and then use the halting gate counter, right? While the value is less, you get from the counter less than what? Less than X. So you wait there, right? Okay, so the set pin out, we have set pin out to set pin input, pin output and input, right? This one. The technique is very simple. Very simple. You go to your scan cube, set it as output, then copy this. Then change it to input, then the code again, copy this one, then you got this one. Very simple. Right? Okay, this one I use what? Equal type, and this one, right? That define equal A, X. Okay, so you just write. You can call this one, set it out, basically you can set it for A, equal A, comma, pin number 16. So automatically you set that for A, in 60, for example. Okay, then check response. Remember the check response? Check response, how to check the response? How to check the response? We wait for 40 microseconds. If you got it low, then bin. Low means what? Low means what? That is the response. Then we delay again for 80 microseconds. Right? If you got high, then the response is good. Now, else we not got. -1 means the response is okay. Means what? Pull down, then pull high, then they touch down. They go down. Pull down, and pull high. Right? The response will be what? Low and high. Okay, now you pull high, then you check the response. After 40 microseconds, the output is still high. No response. 0. If you return 0. You see, I set response to 0. So if the function return 0 means what? There is no response at all. Akan habis. 4 pun tak dapat. Kan? Okay. But if all DPIO read, ESPT blah 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 reads, the response low, but never high. Kan? Macam DP. Kau dapat, tidak datang. Kan? Tak datang. Kau dapat, tidak datang. Itu contoh. Right? So kita nak apa? Down, high. That's good response. Okay? So for the start, first we set the pin as output, see, the ST11 port, the ST11 pin. Then we put down for 18 microseconds. See, 18 microseconds. 18 milliseconds means 18,000 microseconds. Next, pull up the pin and wait. Pull up, and then we wait. Wait. Call this one. We got the response? No response, no. Nothing, right? Okay, so this function to read. So we have how many data inside it? We have 40 data. We have, so this is the ST read, ST read. So this one we read 80 data. So the first data you read 3. Right? 80. Okay, so here, this is simple. Start, then check response, then if the response is 1, then we do, the response is 1, response good, and response good, then what we do? Then we wait till explode while blah 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 read this off. This is the code. If you read it, right, you can understand the code, right? You can understand. So this is the response, when you run it. Okay. So if the signal send the data, I mean there is no response from the DSP, so it will place out that DSP11 failed to respond. Check sum equal to total sum of data. Temperature equal to humidity. When is received correct data? Correct data. Right? So the code actually what? Read the data, check the checksum. If that checksum is correct, then you will the result. So that is the code. What I did. Okay, you can read the reference. So this is some of the reference that we have. For the serial time clock, you can read it. Digital system was output angel, right? And then the digital transistor, right? and then temperature and humidity volume. And the other one is for the LCD. I not put it here, right? For this action. You can get the data sheet by the sheet. This one, right? LCD. So LCD is depend on what? Okay, the LCD is based on this IC. What IC is that? PCF A754. Get the data sheet, then you can understand it. Okay, that's all. Bye bye.